the November 2015 grade 12 question 9. A battery with an internal resistance of 1 ohm and an unknown EMF is connected in a circuit as shown below. A high resistance voltmeter V is connected across the battery. A1 and A2 represent the ammeters of negligible resistance. So this is the positive side and that's the negative. The total current will flow in this direction. And we will have the total current entering that node right there. And then the current is going to be divided. We will have I1 and then I2. So we have I1 entering that junction. So this will be I3 and then we'll have I4 there. The current that leaves this node right there must be what? It must be I1 because that's what was entering the junction. So that is I1. And then I1 and I2 will combine at that point and then will form I total. With the switch S closed, the current passing through the 8 ohm resistor is 0.5. So we have 0.5 passing through the 8 ohm resistor. 9.1. State Ohm's law in words. The current that's flowing through a conductor is directly proportional to the potential difference across its ends, provided that the temperature remains constant. 9.2. Calculate the reading on ammeter A1. So they are looking for I1. Okay. So the 8 ohm resistor as well as the 16 ohm resistor are connected in parallel. For resistors that are connected in parallel, the current is divided. That's why we have I3 and I4, but the potential difference is the same. V is equals to I multiplied by resistance. So we are saying the potential difference should be the same. So V through the 8 ohm resistor should be equals to the V through the 16 ohm resistor. This is I times R, and that is I times R. The current on the 8 ohm resistor is 0.5, and the resistance is 8. We don't know what the current is there, but we do know that the resistance is 16. So I4 should be equals to 0.5 times 8 over 16. So this is 0.25 amps. And then we said that I1 is made up of I3 plus I4. I3 is 0.5, we are given. And we have just calculated I4, which is 0.25. So this is 0.75 amperes. That's what passes through A1. 9.3. If device R delivers a power of 12 volts, so that's 12 watts, calculate the reading on A2. Okay. So we said we're going to combine these two so that they become one resistor. So let's see. So this is the R parallel, which is connected in series with the 20 ohm resistor. Okay, this is I total. It's the total that's entering that node. So we're going to have I1 going up, and then we're going to have I2 going down. Okay, so we currently have, so this is R, and then the power is 12 watts. So we can see that the whole of this is connected in parallel with that. So for resistors that are connected in parallel, they should have the same potential difference, but different currents. So if we can find the voltage that is measured across the ends of that series combination, we will know the potential difference that's measured across R. So let's try and find R across there. We know that the whole of that I1 will pass through the series combination because the potential difference will be divided, but we will have the same current. So we'll calculate the potential difference for the parallel combination, and then we'll calculate the potential difference for the 20 ohm, and then we'll add the two to find the V for that series combination. R parallel should be equals to, so we take the first resistor, that's 8, multiplied by the second one, which is 16, all over 8 plus 16. So I am getting 5.33 ohms. Now I can calculate the potential difference. So V is equals to I multiplied by R. The current that I1, we've already calculated I1, or we were given. We've calculated I1. It is the current that passes through A1, which is 0.75. And then the resistance is 5.33. So I am getting 3.99. So it's essentially just 4 volts. And then I'm now going to calculate the potential difference across the 20 ohm resistor. The current is still the same, which is 0.75 multiplied by 20. So I am getting 15 volts. And then we said the series should be the addition of those two. So it's 15 plus 4, which is equals to 19 volts. So now we have the potential difference across the ends of R, because the potential difference across that should be equals to the potential difference across R, because they are connected in parallel. So we have the power, voltage multiplied by the current. This is 12. The voltage is 19. Then we can find I of A2. 12 divided by 19. I'm getting 0.63 amps. Then 9.4. Calculate the reading on the voltmeter when switch S is open. So when switch S is open, there is no current flowing in the external circuit. So they are looking for the value of the EMF. EMF should be equals to IR plus R. But we don't have this resistance here. So we should change this so that we can use what we have. I multiply by the resistance. So V external is going to be equals to 19. Okay, we said the whole of this and that are connected in parallel, so they should have the same potential difference. Once we combine that and that, and they become one resistor, they will have the same potential difference still. There's no other resistor that's connected, maybe somewhere there or somewhere there. This is the effective resistance. It's the total. So the potential difference must be the 19 that we got. That is the V external. So this is 19 plus the total current should be the current that passes through A1, which is 0.75, plus the current that passes through A2, which is 0.63, multiplied by the internal resistance. Because this is I1 and I2, when you add these two, you should get what? The total current. So this is 19 plus 0.75 plus 0.63 multiplied by 1. So I am getting 20.38 volts.